So today we jump onto the logarithm aspects of integration, and we'll start with the qualifying test of the MIT 2023 integration B. The first question we'll look at is the integral of x to the power 1 over log x, an indefinite integral. And then the next question will be the integral of e to the power x over 1 plus e to the power x times log of 1 plus e to the power x. And then question 9, which is 2 log x plus 1 all times e to the power log x squared. And then question 19, which is log of x over pi over log x to the power log pi times e. So these are the 4 questions we will attempt to solve today. And so, before I begin, I would like to really expand on what a logarithm is. And from Wikipedia and from all literature that you could come by, I think the best defining definition of logarithm is the inverse function of exponentiation, such that if you have a number like 10 to the power x is equals to y, and you take the logarithm to the base 10 of your left side, and you're left with x being equal to the logarithm to the base 10 of y. So you're able to make the exponent part the subject, and how you do that is by using log. And then there's this constant called e. So e to the power x is equals to y in that case. Then if you use a logarithm to the base e, what is called as a natural logarithm, then x becomes a subject, and so what you get on the right hand side is log to the base e of y. Now in the US, when you talk about natural logarithms, we just use log. But for those of us who come from the Commonwealth or from the UK, usually natural logarithms are indicated or symbolizes ln. But for simplicity and for all intents and purposes within this context where we use log, the intention is natural logarithm. So for those of you watching from the UK side of the world, consider that to be ln. So quickly to our first problem of one exponent of a e to the power 1 over log x. So first we let y to be log of e to the x to the power 1 over log x, so that when we take the natural logarithm of both sides, log y, and in this intention, it's for those of you who use ln, consider this to be ln. So on the right hand side, that is log of x to the power 1 over log x. And so using the properties of logarithm, the power inside the log function can be brought to the left side so that it becomes a constant. And so what that means is that log y is equals to 1 over log x times log x. And the log x's would cancel out. And so you're left with log y is equals to 1, and therefore y is equals e to the power 1. And so y is the same as e. So essentially what this means is that our integral of x to the power 1 over log x is the same as just the integral of the constant e. And so our answer is ex plus c, and this is the answer. As simple as that. Then going on to the next problem, the integral of e to the power x over 1 plus e to the power x times log 1 plus ex. So if we let, for example, y to be equal to log 1 plus ex. What that means is that the derivative dy dx is the same as e to the power x over 1 plus e to the power x. And then also that means that e to the power y is equals to 1 plus ex. Now combining those two things, what that means is that then where there is log x, that becomes y, and then where we have 1 plus e to the power x, we get e to the power y. So taking this fraction, the denominator, to the left hand side, e to the power y dy is equals to e to the power y minus 1 dx. And so dividing both sides by e to the power y minus 1, so we get e to the power y over e to the power y minus 1 dy is equals to dx. Then we go forward and now substitute everything in there that we've seen. And so in the numerator, we get, in place of e to the power x, we get e to the power y minus 1. In place of 1 plus ex, we get e to the power y. And as we saw, log 1 plus ex is the same as y. As you can see, the e to the power y minus 1 would cancel out. The e to the power y would cancel out. And you're left with 1 over y dy as your integrand. And then what happens that when you integrate that, you get log y plus c, but we know what y is. Y is the same as log 1 plus e to the power x. So our answer is the logarithm or natural logarithm of 1 plus e to the power x. So that was number 2. Moving forward, number 9. Number 9 says the integral of 2 log x plus 1 times e to the power log x squared. Now, this is a little bit more complicated. First of all, I'll be looking at the most complicated portion of the integrand, and that is e to the power log x squared. So when I try to differentiate that, what I get is log 2 log x over x times e to the power log x squared. And so what 2 log x plus 1 e log x squared is the, in place of this 2 log x, is the derivative of, is x times the derivative of log x squared over dx. And where we have 1 here, we can say that, oh, that is the same as the derivative of just the variable x. And when you look at this formalism here, this looks like the product rule differentiation as what we have as the integrand here. So essentially what this means is that our answer here is the product of this x and this e to the power log x squared. That's our answer. Simple as that. X times e to the power log x squared plus c. This is the answer. Then the last question, question 19, which is log x over pi over log x to the power log pi e. So just simplifying the integrand log x to the power over pi using the properties of logarithm is the same as log x minus log pi over log x, and again using properties of logarithm, whatever is multiplied within the log function is the same as the addition of the separate logs of the whatever is in the function. So as you can see, this becomes log pi plus log e. And then law of exponents means that you can always multiply whatever is at the base with respect to any addition of the exponents. So if you, for example, we have log pi plus log e, this is the same as log x to the power log pi times log x times log to the power log e. And log e here, since it's a natural logarithm, same base as whatever is being considered, that means that this entire this is the same as 1. So we have log x minus log pi over log x over log pi times log x to the power log e. And as I said, the log e is the same as 1, so that remains as log x to the power 1. And then you can go further to simplify it. We divide log x, the first part of the equation here, and then on the second part, the log x remains the denominator. So this is what we have obtained. And then again, as I said previously, looking at the most complicated part of the function, which is 1 over log x to the power log pi. When I differentiate that, we get negative log pi times log x to the power minus log x minus 1 times 1 over x. So what that means is that we have in the numerator log pi times x over x times log x to the power log pi times log x. This provides us further insight. So this provides us further insight in the sense that what we had previously here, as we can see, this part here is the same as x times the derivative of this first part of the equation. So essentially we can express what we had previously as 1 over x log pi to the power log pi times 1, which is the derivative of x, plus x times the derivative of 1 over log x to the power log pi. So this, as you can see, allows us to see that whatever the integrand is a product rule derivative of a product of x and 1 over log x to the power pi. So the integral log x over pi over log x to the power pi times e is x over log x to the power log pi plus c. And that is the answer. Again, much appreciation for hanging out with me today and solving these very interesting problems. For those of you who have not subscribed to our channel, I highly encourage you to subscribe to our channel because we actually do solve some very, very cool problems. But above all, we'll give you notifications every time we come up with solutions. Thank you. So we're going to try to solve the first problem using Python. So I'm going to use an online compiler called Jupyter. That's a notebook that allows you to compile Python code online. So I'll just go to the browser and type Jupyter online, and then I'll try Jupyter, and then go down to notebook. I'll select that notebook. And the next thing I'll do is under file there, I will select notebook. And that should allow us to use notebook. So I'll select that kernel. And then one thing I'm going to try and do is I'll import the NumPy library as np. That allows you to manipulate arrays. I'll also import the SymPy library as SMP. I'll import SciPy, SP. Try to import matplotlib, lib.pyplot as PLT. From SciPy.integrate, I'll import code library from the SciPy.integrate as well. I'll try to import cumulative trapezoid. And for those of you who have done applied math, will probably understand what the cumulative trapezoid does. And then I'll run the selected cells. So it seems like our importation has gone on well. And then I'll go ahead and say, okay, define XSS symbols in library SMP. There is something that allows you to define X as a symbol, and it should be real. And then F is our function that is the power. So for those of you conversant with Python, you will know that when you are trying to invoke powers, you use double asterisk. And so now our function is x to the power 1 over log x. So we use a function in the SMP library known as logarithm, natural logarithm. And so that's our function. So let's run this, select it. Seems that is fine. Then the next thing we want to do is under the SMP library again, we're going to integrate f with respect to x. So let's see what this will result. So as you can see, our answer is x, ex. There's no constant, but that's something good. So for problem number 2, I think we'll keep x as it is. Then we'll define function f1 is equals to an SMP function exponential of x. Let me just go. Okay, let's just go ahead and do that, and then I'll double, and then over another set of bracket 1 plus an SMP function exponential x times the SMP function of logarithm x 1 plus another SMP function exponential of x. Okay, let's see whether that seems to be okay. So the next thing we're going to try and do is integrate that function f1 with respect to x, and let's see what it gives us. And as you can see, the integral there is log of logarithm of e to the power x plus 1. Now, it doesn't give you the constant, but that's amazing because that's the answer we got, just minus the last constant. So for our last function, we'll call it function f2, which is equals to SMP logarithm of, we first of all have to import a library called math. Okay, let's see whether that is good. And then let's see whether pi is something that is supported. Yes, it's supported. So we're going to say, okay, function f2 is equals to SMP of logarithm of x over s okay? And that is over first SMP log of x times is actually to the power of SMP log of plus over math dot pi. Let me just put this in bracket just in case times SMP dot exponential of 1. Okay, let's see whether I can run that. Seems to be okay. And then the next step is now to integrate that function f2. f2 with respect to x. Let's run, select it. And let's wait and see. It's taking a little bit longer. But this is a very complicated integral for this machine. It's probably given up on us. Oh no, yeah. So it gave us this very complicated answer, which is not the answer. And I think the problem is it tried to interpret this last part, the power of log, and it did fail. I'll probably also show you some other softwares that let's probably try Wolfram Outward and see whether that could. I'm willing to bet that that one would also fail in integrating. So we have we want log of x over pi divided by of x to the power log of pi times p dx. Dx. And let's run this and see. So the numerator has been interpreted well, but it fails to interpret the denominator in terms of just how to handle the power. And I don't know if there's a way around this, but as you can see, it says no result found in terms of standard mathematical function. There are things that we as humans can solve, but machines find it a little bit harder to handle. So I guess there's an edge for humanity over computers to some point. But also it just could be the failure for the computer to really interpret the input information you're feeding in. So that's it. Thank you so much. And yeah.